Hello everyone. Today we will be discussing a very interesting problem on classical mechanics. Suppose you have a solid cylinder and this solid cylinder is rolling on a horizontal surface. So let me give a name of this horizontal surface. Suppose the horizontal surface is XP. And at the end of the horizontal surface you have an inclined plane PQ. PQ is inclined at an angle alpha with the horizontal. This is a solid cylinder. The solid cylinder has a radius smaller and initially the center of mass of the solid cylinder has some velocity V0. It is undergoing a pure rolling motion. Now when the cylinder, after rolling on the horizontal surface, transits into the inclined plane at the point P, in order that it must not jump, if the cylinder has to roll on the horizontal surface and from the point P very smoothly transit into the inclined plane so that it does not jump at the point P, which is a very sharp transition, then what should be the initial velocity, or what can be the maximum value of initial velocity V0? This is the problem. So for the cylinder which is right now rolling on the horizontal surface XP, when it transits into the inclined plane PQ, we want to find out that what should be the value of V0 so that when it transits from the horizontal surface to the inclined plane at the point P, it does not take a jump. So what happens? Let us see the point P. The point P is very crucial. So when the cylinder comes to the point P, at one moment it is there on the horizontal surface and at the next moment it is there on the inclined plane, right? So if I see this particular diagram, the black cross section, there the cylinder is having a point of contact P and it is on the horizontal surface. And if I see the blue cross section, there the cylinder is having point of contact P but it is on the inclined plane. So what is basically happening here? You please see. So actually the center of mass C, and suppose this is P, this distance is R. This center of mass here, as you can see, it has come from C to C dash, is basically rotating in a circular trajectory. And what is the center of the circle? The center of the circle is the point of contact POC. So point of contact is P. So P is the center of that circle, and the center of mass during this transition moves in a circular arc. So C basically comes here. Say maybe I can call that this particular point is C dash. So C comes to C dash. Okay. So what can I say about C dash? That this is also the radius. See, P to C dash is the radius of the circle, and this is the circle in which the arc, in which the center of mass is rotating. P, which is the point of contact of the cylinder, is the center of this circle. Now please see, if you consider this particular angle alpha, so definitely weight of the particle will act in the downward direction mg. So this line PC dash is perpendicular to the inclined plane. So of course in this particular direction this angle must be alpha, so we will get mg cos alpha, and we will get mg sin alpha in this direction. Okay, for your reference again I am telling you, say this is mg, in this direction mg sin alpha, and in this direction if I consider P and C, in this direction which is perpendicular to the plane, you have mg cos alpha, right? So if this angle is alpha, this angle must be alpha. This is 90 degree. So cos alpha is base by hypotenuse. How much is the hypotenuse? How much is this? This is R. If this is R, then this distance is how much? R cos alpha. Please get familiarized with the geometry at first. So center of mass has lost a vertical height this much, and how much is this vertical height? R minus R cos alpha. So this is R into 1 minus cos alpha. So center of mass has basically come down by R into 1 minus cos alpha. Now if I see initially when the cylinder was rotating on the horizontal surface, so initially total kinetic energy of the cylinder is what we can write, half m v naught square plus half into cylinder's moment of inertia about the center of mass. So I can write it half m r square into omega naught square, where omega naught is, where I can write v naught equals to omega naught into r for pure roll, for pure rolling motion. So therefore what we can write, so it implies that initial kinetic energy is half plus 1/4 means 3/4 m v naught square. So this is my equation 1. So this is the initial kinetic energy of the cylinder when it was rolling, having a pure rolling motion on the horizontal surface. Now you could have also found out the kinetic energy considering instantaneous axis of rotation passing through this point. So in that particular case you would have done only rotational kinetic energy about the instantaneous axis of rotation passing through this POC. In that case directly you will get 3/4 mv square. So this is an easier approach. Now when the cylinder takes a turn about the point P, pivoting point P, it turns into the inclined plane from the horizontal surface. Then what happens? It has velocity v, which is not v0. Why its velocity has changed? Because center of mass has gone down. As center of mass has gone down, some gravitational potential energy is lost, right? So we can very clearly see here, say loss in gravitational potential energy equals to mg into loss in height r into 1 minus cos alpha. Say suppose this is my equation 2. Now when it takes a turn, what happens there? Let's see. So till here everything is clear, I guess. Now see, when this particular center of mass is following this circular arc, it is keeping contact with the surface. So because of that there will be a normal reaction acting in this direction. So there is normal reaction plus what is the radius of this circle, r. So if you go and sit on this center of mass, say at the point C dash, you go and sit at the point C dash, that is you are on the C frame, then there will be an outward, radially outward centrifugal force. Okay, so n and mv square by r, they are acting in radially outward direction, and mg cos alpha is acting in radially inward direction, right? So from here what we can say, that in equilibrium n plus mv square by r equals to mg cos alpha. Okay, we will come to that. So what we can write, that in equilibrium n plus mv square by r equals to mg cos alpha. Okay, so this is my equation 3. I am just collecting equations. Now when the cylinder has taken turn on the inclined plane, it has got some kinetic energy. And how much is the kinetic energy? The cylinder has taken a turn with the instantaneous axis of rotation passing through the point P. Now see very carefully, if you consider this particular point P and the cylinder is rolling about this particular point of contact P, then what is the kinetic energy it has? Kinetic energy is half I omega square, and that I is actually calculated about the point of contact. Okay, so in this particular case, so what we can say, the kinetic energy final when the cylinder has transited, it has made the transition from horizontal surface to the inclined surface, we can write half I about POC into omega square. So this is equals to half into I POC. I POC is what? mr square by 2 plus mr square. Okay, this one we have got by parallel axis theorem, because moment of inertia about this axis is mr square by 2, about this axis mr square by 2 plus mr square. So this into omega square. So of course you will get 3 by 4 m r square omega square. Now as here also pure rolling motion occurs, so v equals to r omega, so therefore k final equals to 3 by 4 m v square. So this is the final kinetic energy of the sphere. Final kinetic energy of the sphere. Okay, now let's see the physics behind it. What is happening here? So when the cylinder is making of the cylinder, sorry, sometimes by mistake I am telling sphere, maybe, please excuse me. Now when the cylinder makes a transition from the horizontal surface to the inclined surface, then what is basically happening? The kinetic energy is gained by the cylinder, and that gain in kinetic energy is due to loss in gravitational potential energy. So by using equation 1, 2 and 4, what I can say, loss in gravitational potential energy is equals to kf minus ki, which is gain in kinetic energy. And why this happens? This happens because of energy conservation principle. Okay, so I am rubbing off this particular part, and we will proceed with this. I hope you have understood till here. So now you see, so by ECP, what we can write, ECP means energy conservation principle. By ECP, what we can write, kf minus ki equals to mgr into 1 minus cos alpha. Okay, mgr into 1 minus cos alpha. Okay, there you saw that the height which was getting the loss in gravitational height was r into 1 minus cos alpha. So kf was 3 by 4 m v square minus v naught square equals to mgr into 1 minus cos alpha. So you can cancel off m. So from here basically we get v square minus v naught square equals to 4gr by 3 into 1 minus cos alpha. Okay, this is my equation 4. Now you see once again equation 3. If the cylinder takes a jump at the point P, suppose we are considering cylinder while rolling from horizontal surface to inclined surface takes a jump. So if it takes a jump, it loses contact with the inclined surface, and as a result normal reaction vanishes. So if the cylinder jumps at P, at the point P, then normal reaction must be 0. And if normal reaction is 0, so it implies m v square by r equals to mg cos alpha. So you can cancel off, so you get v square equals to gr cos alpha. Now you put this value, say I am calling this one equation 5, put 5 in equation 4. Put 5 in 4, and from there you will get v naught square. V naught square equals to v square minus this, v square is gr cos alpha minus 4gr by 3 into 1 minus cos alpha. So this is nothing but gr cos alpha, so I can call it 3gr cos alpha minus 4gr plus 4gr cos alpha whole divided by 3. So from here what do we get? We get v0 equals to square root of, you can take gr common, so gr by 3, and within bracket what we will get, 3gr cos alpha plus 4gr cos alpha, so 7 cos alpha minus 4. Okay, so this is the expression for the velocity. Now if the cylinder, if the initial velocity of the cylinder has this value, then what happens? It takes a jump. Okay, so it is like a critical condition that when the initial velocity of the cylinder attains this value or has a value greater than this, then the cylinder will take a jump at the point P. So in order that the cylinder makes a smooth transition from at the point P from the horizontal surface to the inclined surface, its initial velocity must be less than this critical value. Okay, so if the initial velocity of the cylinder has a value which is less than this, then it maneuvers the turn at the point P very smoothly without taking a jump. So this particular concept has a very interesting, a very intriguing part, which is that you see at the point P, when the cylinder makes the transition, the center of mass is basically following a circular path. So this is the concept of pure rolling motion. Okay, so instantaneous axis of rotation passes through this point. So any rolling body can be visualized like this, that the instantaneous axis of rotation passes through the point of contact, and the center of mass of the body is making a circular turn about the POC. So I hope this particular problem you found interesting and it helped you to brush up some fundamental concepts of classical mechanics. Thank you very much for paying your kind attention. Thank you.